Hello. Today we will analyze the frequency response of the LJ Technical Systems servo system. The objective of this practice is to obtain the theoretical and experimental frequency response of the open-loop system. Along with this, we will apply the Nyquist criterion to determine the range of values of a proportional controller so that the system is stable, and we will verify it experimentally. But first, before beginning to analyze the frequency response of the system, it will be explained what a frequency response is and how its transfer function is obtained. The frequency response is the steady-state response of an unstable system to a sinusoidal input. The output of the system will be another sinusoidal signal of the same frequency but multiplied by a gain and shifted in phase by an angle. In the figure, it can be seen an example where the input is shown in red and the output in blue. The output is the same signal but multiplied by 0.6 and shifted 45 degrees. The system transfer function can be used to compute the amplitude change and the phase shifting. To do this, the transfer function needs to be evaluated at the signal frequency. The result is a complex number. Its amplitude corresponds to the amplitude change while its argument corresponds to the phase shift. The frequency response is the steady-state response of an unstable system to a sinusoidal input. The output of the system will be another sinusoidal signal of the same frequency but multiplied by a gain and shifted in phase by an angle. In the figure, it can be seen an example where the input is shown in red and the output in blue. The output is the same signal but multiplied by 0.6 and shifted 45 degrees. Following with the example before, we will analyze how the module and phase angle are obtained. The magnitude corresponds to the ratio between the input and output amplitudes, while the phase angle is the displacement of the output with respect to the input. Be careful, as in this case, from the graph it would be obtained the displacement in time. It must be converted to radians or degrees multiplying it by the signal pulsation. There are different diagrams to represent the frequency response. Most popular ones are Nyquist, Bode and Nichols diagrams. In this practice, the first two diagrams will be analyzed. In the following, the continuous time Nyquist and Bode diagrams will be explained. The Nyquist diagram is a polar diagram where the module and phase angle of the system along omega is shown, varying it from 0 to infinity. In this example, the continuous time plant transfer function is evaluated in a generic frequency omega. For each frequency a complex number is obtained. By computing this value at different frequencies, we obtain different points in the polar diagram. By linking all the points, we obtain the representation from omega equal to 0 to infinity. The Bode diagram is divided in two different diagrams, the magnitude and the phase diagram. The magnitude diagram shows the evolution of the transfer function module at different frequencies while the phase diagram shows the evolution of the transfer function argument. The x-axis contains the frequency in logarithmic scale, the magnitude is represented in decibels while the phase is shown in degrees. In the following, how the Bode diagram, for our continuous plant transfer function is built, will be shown. For each frequency, the module and phase are calculated and plotted on the graph. Finally, by linking the points, we obtain the Bode plot of the system. Although the frequency response concept is the same both in continuous and discrete time, how the gain and phase are computed is slightly different. In the following, how the discrete time frequency response is computed will be shown. For that, the continuous transfer function must be discretized using the Z-transform. In this example a sampling time of 0.01 seconds will be used. Once this has been done, a new transfer function is obtained. This one uses the Z variable instead of the S1. The relation between the Z variable and the frequency uses the exponential and the sampling time. The steps followed from this point on, are the same as before. By substituting different omegas in the obtained formula, we will obtain the magnitudes needed. If we compare the continuous and the discrete Nyquist diagrams, we can see, they are very similar in the low frequency range while they begin to differ in the medium and high frequency ranges. In the discrete time case the curve crosses to the third quadrant. The discrete time Nyquist diagram is obtained by evaluating the discrete system's transfer function in different frequencies. As in the continuous time case, a complex number is obtained in each frequency, and by linking all the points the Nyquist plot is obtained. In the discrete time case, frequencies are swept from 0 to pi divided by the sampling time. As we can see, the Bode diagram also changes a bit when discretizing it. Firstly, the range of frequencies is different. Secondly, the values in the medium and high frequency ranges change significantly. As in the continuous time case, the Bode diagram is obtained by calculating and linking the gain and phases for different frequencies of the complex transfer function obtained previously. In this case too, the frequencies are swept from 0 to pi divided by the sampling time. In the following, a set of experiments to experimentally obtain the plant frequency response will be performed. A sampling period of 0.01 seconds will be used. To perform this Simulink model has been implemented. A 2V sine signal with different frequencies is generated. The response of the motor to these signals will be analyzed. But first let's see a video showing the motor response to these type of signals. In this video it is shown how the motor behaves in front of two sinusoidal inputs. The first one is a 2 volts 0.25 Hz sine. The second case is a 2 volts 2 Hz sine. Calculating the gain change and the phase shift produced with each frequency, we obtain the experimental Nyquist diagram. As we can see, in this case, at low frequencies, the phase shift and gain change produced are very small. As we can see, the higher the frequency, the shorter the gain and the bigger the displacement. Once made the experiment for different frequencies, we can see how the experimental Nyquist diagram resembles the theoretical one. The small differences come from the measurement errors and non-modeled dynamics. Many times, to calculate the stability of a control system like the one presented in this image, the Nyquist criterion is used. For that, the formula shown is implemented, where Z is the number of unstable closed-loop poles, P is the number of unstable open-loop poles, and N is the number of encirclements to the critic point. From the Nyquist diagram, we can analyze whether the system is stable or not. As we can see on this figure, if the system crosses the critic point from the right, the system will be stable. While, if the diagram crosses the critic point from the left, the system will be unstable. It is worth to mention that those systems represented on the Nyquist have no poles on the right-hand plane of the S-plane, which means P is equal to 0. Switching to our case, we can know whether the system is stable or not by the formula on the figure. As we have seen on the Nyquist plot, in our case, as there is no encirclements in the critical point, the system will become unstable when the equation on the slide meets. We can see that multiplying the open loop with a gain k, we can move the closed loop pole's position to the left-hand plane, so we can know the maximum gain a proportional controller can have before obtaining an unstable system. As we can see, when plotting the open-loop Nyquist diagram of our plant with different gains, the scale of the diagram increases, being closer and closer to the critic point. Increasing the gain, there will be a point that the system passes from a stable region to an unstable one. If we zoom onto the critical point, we can see how the system with a proportional gain of 65 is unstable. In order to experimentally validate these results, the following Simulink diagram has been made, where the output of the system has been fed back and a proportional controller has been created. So, we will analyze the responses in the stable and unstable ranges. On the box in the right, you can see the code implemented to obtain the gain limit. These figures show the simulation results for Kp equal to 5. As expected, the system behavior is stable. As we can see, the experimental results are qualitatively similar to the ones obtained in the simulations. In this video, we can see how the motor behaves with a proportional controller equal to 5. When we apply a Kp value greater than 63.42, in this case 65, we can see that the simulation of closed-loop system behavior becomes unstable. In this figure it can be shown the experimental results obtained for the same case. As it can be seen, the results are qualitatively different. In this case, the output is following the reference, and apparently the system behavior is stable. The main difference with the simulation model is that in the experimental setup the control action is saturated and can only take values between -5 and 5 volts. Consequently, the closed-loop behavior cannot be explained in terms of the linear system. In this video, the closed-loop experimental behavior can be observed. As we can see, the motor has a constant velocity when applying different references instead of getting unstable as seen in the simulation. This comes from the fact that the control signal has limitations. The control signal is limited to and -5 volts, so the motor cannot take higher velocities. Due to the high gain in the proportional controller, the control action switches between different values. To conclude this practice, the theoretical Nyquist diagram for the position output has also been obtained. For that, the original continuous time transfer function is recovered. This system model is discretized with a sampling time of 0.01 seconds and then transformed into the isochronous function. Using MATLAB, the following Nyquist diagram is obtained. This diagram is qualitatively different from the velocity one. The curve begins at infinite due to the existence of an integrator in the transfer function. To determine if the closed-loop system will be stable or unstable, we need to know the relative position between the -1 point and the curve. Due to this, a zoom around the -1 point will be performed. It can be seen that the curve crosses the real axis at the right of the -1 point, which means no encirclement is produced and the closed-loop system will be stable. The gain and phase margins are both positive. As in the case before, when closing the loop and increasing the gain of the proportional controller, the system gets closer to the instability. And as we can see, in this case, for a proportional gain of 25, the system is already unstable as it crosses the critical point from the left. In order to experimentally validate these results, the following Simulink diagram has been made, where the output of the system has been fed back and a proportional controller has been created. So, we will analyze the responses in the stable and unstable ranges. These figures show the simulation results for Kp equal to 2. As expected, after some time, the system will follow the reference. As we can see in the experimental result, a stable closed-loop system is obtained. The differences of the graphs come from the non-modeled dynamics. In this video, we can see how the motor behaves with a proportional controller equal to 2. When we apply a Kp value greater than 23, in this case 25, we can see that the closed-loop system behavior becomes unstable. In this figure it can be shown the experimental results obtained for the same case. As it can be seen, the results are qualitatively different. In this case, the output is following the reference in an oscillating way and apparently the system behavior is stable. The main difference with the simulation model is that in the experimental setup the control action is saturated and can only take values between -5 and 5 volts. Consequently, as in the velocity control case, the closed-loop behavior cannot be explained in terms of the linear system. In this video, the closed-loop experimental behavior can be observed. As we can see, the motor oscillates around the reference instead of getting unstable as seen in the simulation. This comes from the fact that the control signal has limitations. The control signal is limited to ±5 volts, so the motor cannot take higher control values. Due to the high gain in the proportional controller, the control action switches between those values. In addition to these experiments, students analyze the different margins and parts of the Nyquist diagram and the system analysis using the theoretical Bode diagram.